Hello everyone, I Anurag Singh will be presenting our work Improving Semi-Supervised Domain Adaptation using Effective Target Selection and Semantics. In this work, we aim to improve the performance of common semi-supervised domain adaptation algorithms by incorporating a few simple yet effective modifications which address specific drawbacks of previous works on semi-supervised domain adaptation. Usually, semi-supervised domain adaptation needs labeled target data, which is often manually annotated, and SSDA performance is very dependent on the choice of this labeled target data. Since the choice of label data is so critical, therefore it becomes imperative that we select the label target examples carefully so as to maximize the performance of domain adaptation. In other algorithms, the target samples which are to be labeled are chosen manually, which requires a lot of time and effort. In our proposed approach, instead of choosing the target samples manually to label, we propose an active learning framework which chooses the target samples based on criteria of diversity and model classification uncertainty to maximize the performance. We have a labeling budget, so initially we start with the unlabeled target data. Using our active learning approach, we select diverse selected samples, which are then labeled via an oracle. So, how do we actually choose the target samples to be labeled? First, we start by modeling the domain adaptation classifier uncertainty based on the class prototype movement, which can also be called as the prototype speed. The class prototypes are nothing but the final layer weights of our classifier. The class prototype weight of a mod of class C at iteration T as defined as WTC in the blue bounding box, and the class prototype at iteration T-1 is defined as WCT-1. First, we start with computing the distance between the prototypes of iteration T and T-1. For more robustness, we compute the moving average over L time steps, where the most weight is given to the last time step for the iteration at which we calculate the distance between the class prototypes. In our entire training schedule, we calculate the distance for the class prototypes at 2500, 5000, and 7500 iterations. So now the distance is computed for all the class prototypes, and then we compute the mean of the distances of all these class prototypes as indicated in the red bounding box. Eventually, we compute the class-wise uncertainty coefficient beta by simply checking if the particular distance is greater than the mean distance, which assures us that the following prototype has been more uncertain during its training schedule than rest of the prototypes. And for other examples where the distance of the change is less than the mean, we simply assign beta to 1. In this slide, we see the plots of the moving average of the prototype speeds for iteration t equal to 2500, 5000, and 7500. These are the iterations at which we choose the target samples to be selected for 3 short semi-supervised domain adaptation setting. We choose C samples at each of the 3 iterations, where C is the number of classes in our algorithm. It can be noted in each of these graphs that the per class movement of the prototypes is different for each of the classes, which says that the prototype speeds at the prototype adaptation rate for each of the classes is different, and there will be some examples which will have prototype adaptation rate greater than the mean, and there will be some examples which will have prototype adaptation rate smaller than the mean. The second criteria which we choose to consider the target samples to be labeled is the diversity of the target samples. To obtain diverse samples from the pool of unlabeled target samples, we first apply k-means clustering over the unlabeled target examples with 2 C clusters. We simply choose twice the number of classes as the clusters to incorporate for within the class relationship of the target examples. After performing k-means clustering, we find the 2 C samples which are closest to these cluster centroids. This is denoted by calligraphic X UT divergence. to obtain the class prediction of each sample in this set is the next step. After the class predictions have been obtained for each of these samples, we calculate the distance of this uh, sample in this set with its nearest prototype, which is denoted as DWTC, xi diversity ut, which is multiplied by the corresponding class uncertainty coefficient to get the final uncertainty. After these two C final uncertainties have been calculated, we choose the top C diverse samples from them, and this is repeated until the labeling budget has been exhausted. This slide shows our unified method star algorithm by gluing all the individual components together. We also address some other points in the semi-supervised domain adaptation literature to further improve performance. For the label-rich source domain, we address class imbalance present by using class balance focal loss on the source examples, which is denoted here by LCBF. We also weigh the target samples in the loss function based on their predicted class probabilities, which is denoted by the weighted entropy LUH. For better unification of the source and target examples during domain adaptation, we incorporate pre-trained word embeddings of the class names and initialize the class prototypes with them, which is shown here as the W, which is the class prototypes, has been initialized with the GLOW 50 dimension vectors. These semantic embeddings not only help in the unification of both source and label target in the embedding space, but they also help in the computation of the distances for the active learning framework that we proposed, because this reduces the dimension of the prototypes to the embedding space instead of the deep representation space. We use three commonly used datasets to benchmark our method, namely DomainNet, which has 4 domains, 126 classes, and 7 domain adaptation scenarios. Office Home, which has 4 domains, 65 classes, and all 12 domain adaptation scenarios. Office 31, which is a relatively small dataset with 3 domains, 31 classes, and 2 domain adaptation scenarios. These are our results on DomainNet and Office Home. On DomainNet, we perform our experiment using ResNet 34 as the backbone. It can be seen that the proposed star approach performs better than most of the state-of-the-art approaches on almost all settings, with the mean classification accuracy of 70 for one shot and 73.2 for 3 shot. With AlexNet as a backbone on Office Home, proposed star approach also outperforms most of the state-of-the-art methods on almost all the settings, with the mean as 52.54 for one-shot setting and 57.03 for three-shot setting. For further analysis of our method, we conduct an ablation study using ResNet 34 as a backbone on DomainNet dataset for R2S and C2S settings. It can be seen that each component of our method, actively labeling the targets, semantic initialization, and weighing hard target samples, contributes to the performance of our method. Since we also address the class imbalance issue in domain adaptation, we conduct an experiment to evaluate class-wise average performance of lowest 30, which is the minority classes, and highest 30, which is the majority classes, on DomainNet R2S setting for 3-shot scenario. This is also done using ResNet 34 as a backbone. We compare our method's lowest and highest 30 class-wise performance with another state-of-the-art method. It can be seen that our method significantly improves and addresses the class imbalance issue. Thank you for your attention.